So now you take a beam, which is a two-span continuous beam, which has fixed end at A, and actually this is a roller support, hinged end or simple end at the B and C. So first you have to identify the loads. So the first span has a concentrated load which is not at the mid span. The second span has a uniformly distributed load. So in this that I have given a list of fixed end moments that you have to refer. Then you write the fixed end moments, that is MFAB. This is not MAB actually. This is MFAB, which is equal to minus WAB squared by L squared, which is minus 44.44 kilonewton meter. And at the right end we have the moment 88.89 kilonewton meter. So here it is anti-clockwise, here it is clockwise, the fixed end moments. Similarly, for the second span we have UDL. So the magnitude of fixed end moment is WL squared by 12. So here it is negative. At support C it is positive. So first we are assuming that there is no rotation at the joint. All joints are assumed as fixed. Next you have to identify the unknown rotations. So joint by joint you have to identify. So here there are 3 joints. So joint A is a fixed end which restrains all the degrees of freedom. Joint B is a simple support which has restrained against translation. So there will be some reaction will be there, but it does not restrain the rotation. So there will be some rotation, that is theta B. Similarly at joint C also a simple support which has theta C. And here, since there is no continuity at support C, ultimately the moment at C is equal to 0. That we will check after solving this problem. We will check. Next, after finding the fixed end moment and identifying the rotations, we have to formulate the slope deflection equation for each span. So here there are 3 join and 2 span. Each span will have 2 equations corresponding to both the ends, each end. So MAB and MBA for the span AB, and we have MBC and MCB for the span BC. So you have to formulate the slope deflection equation. Remember that in this problem there is no settlement of support. Okay, you no need to add the term 3 del by L. So we have MAB is equal to MFAB plus 2A by L into 2 times theta A plus theta B. So you substitute the fixed end moment what we have got for the span AB. Then you write these equations. Similarly, we have to write all the slope deflection equation for the entire beam. Then already we know, based on the support condition, the fixed end will have 0 slope. The rotation at support A is 0. That you can eliminate theta A from these equations. Now you see the unknown displacements in this beam is theta B and theta C. We have 2 unknowns, and we have 4 slope deflection equations. All the 4 equations are expressed in terms of only unknowns. See here, theta B and theta C. Clear? While writing the slope deflection equation, you please remember that the sign of the fixed end moment, at the left hand it is negative, at the right hand it is positive. Some students may forget to substitute They write only the magnitude, they forget to substitute the sign, whether it is positive or negative. Similarly, for the final end moment MEB, the first letter is A, the second letter is B. That means A is the near end, B is the far end. So while writing the slope deflection equation, you should write 2 times the near end, that is 2 times the theta A, and 1 times the far end, that is theta B. Similarly, while writing MBA, so in this equation, B is the near end. So it appears in the first place, A is the far end. So while writing the equation, you should write 2 times theta B and 1 times theta A. Similarly, for MBC, B is the near end, C is the far end. So we have 2 times theta B and 1 time theta C. Similarly, for MCB, 2 times theta C plus theta B. Then you eliminate all the known rotations. Next, you have to write the slope deflection. After writing the slope deflection equation, you have to write the equilibrium conditions at any joint. For example, in this problem, at joint B, the sum of moment is equal to 0. That is MBA plus MBC is equal to 0. So these equilibrium equations we have to write for the joint corresponding to unknown displacements. So in this problem, theta B and theta C are the unknown rotations. So you have to write the equilibrium condition. You can write the equilibrium condition for the support B as well as C. So in this case, at support B, MBA plus MBC is equal to 0, and for support C, MCB is equal to 0. There are two equations of equilibrium. See, in this problem we have two unknowns, theta B and theta C, and we have two equations of equilibrium. So theoretically you can solve this problem. You can find the unknown rotations by solution of simultaneous equations. So you substitute all the slope deflection equation in this the equilibrium equation. Like MBA, already we have MBA as 88.9 plus 2a by 3 into theta B. So you substitute that equation in this, and finally you will get a long equation. Similarly, we have MCB is equal to 0. So like this, you will have some simultaneous equations in terms of the unknowns. So by solving these equations, you will get the final rotations. That is, theta B is minus 20.83 divided by A, and theta C is minus 41.67 divided by A. So after finding this unknown rotation, you have to substitute these rotations into the slope deflection equation to find the final end moment. So for MAB, in this case, minus 51.38 kilonewton meter, MBA is 75 kilonewton meter, and MBC minus 75 kilonewton meter, and MCB is 0. Here K should be small, remember that. So these are the final end moment. You see here at the intermediate joint, that is B, the magnitude of the moment is same. Magnitude of the moment is same. Only the nature differs. So here it is clockwise for MBA, and for MBC it is anti-clockwise. So at any intermediate support, the adjoining moments are opposite and equal. Okay. Now you notify these moments like this. So for this span AB, we have 51.38 anti-clockwise, 75 clockwise. Similarly, for the span BC, we have 75 anti-clockwise, and support C we have 0 moment because it is a simple support. See here, MCB is finally it is 0. So this is how we can solve the any continuous beam or frame by the slope deflection method. Then we have to draw, after finding the fixed and final end moment, we have to draw the shear force and bending moment diagram. So to draw the shear force diagram, again you have to apply the principle of superposition. First you have to find out the support reactions. So here there will be support reactions due to applied load, like 100 kilonewton and a UDL of 20 kilonewton meter. So that you can find out from the basic principles. Sum of E is equal to 0, sum of M is equal to 0. That you already studied in your second year. Okay. So for example, this 100 kilonewton, which is not at the midspan, which induces a support reaction of PB by L at A and PA by L at B. Similarly, this UDL will induce a reaction of WL by 2. So first you have to write these reactions due to applied load. Then there are end moments. So these reactions has been found out by considering the simple supports. There is no continuity, there is no fixed. So these are the simple support reactions. So in addition to that, we have end moments. Now we have to find out the reaction due to these end moments. So now we take the span AB, we have two moments. One is anti-clockwise, the other one is clockwise. So we find the net moment. So you might have already studied, for any simply supported beam when it is subjected to a moment, the support reaction is net moment divided by span. So if the net moment induces anti-clockwise, when it has anti-clockwise sense, the support reaction should induce a clockwise sense. Okay, so at support A it has to be a upward direction, the reaction should be upward, and at support B the reaction should be downward. So based on the net moment available at the span, the support reaction should develop a anti moment. When the span moment is clockwise, moment due to reaction should be anti-clockwise. When the span moment is anti-clockwise, the moment due to support should be clockwise. So to get the net reaction, you have to add the reaction due to applied load as well as the reaction due to net moment in the span separately. This is called principle of superposition. So finally we will have the reactions RA, RB, and for the second span RB and RC. So now you can easily draw the shear force diagram. And to draw the bending moment diagram, we have some conventions. See, the sign convention for bending moment is sagging moment is positive. That means the sagging moment will induce only when there is a anti-clockwise moment at the left hand and clockwise moment at the right hand. So while drawing the bending moment diagram, we consider sagging moment as positive, sagging moment as negative. But while solving this slope deflection method, we have clockwise moments are positive, anti-clockwise moments are negative. So how to draw this final bending moment diagram? Okay. So first what you have to do, you have to superimpose simply supported moment diagram onto the fixing moment diagram. First you have to draw the fixing moment diagram. So the fixing moment diagram is negative. that you have to draw above the datum. For example, support A, it is minus 51.38, so you draw it above the datum. And for the B support, we have two moments. MBA is 75 kilonewton meter, so that also you have to draw above the depth. Why? Because here the sign convention is different for the n moments. So for the bending moment, sagging bending moment, if you take the left hand side, you will have anti-clockwise moment. So you should take for a span at the left hand side, if there is an anti-clockwise moment, you should consider it as a positive. But we have taken in this case clockwise are positive. So to eliminate this, you should substitute negative, that is the above the datum you have to mark the ordinate. So if you take a span, left hand side minus, right hand side plus. These are the sign convention to be followed in slope deflection method. That is the above datum. Usually above datum we will mark positive values, but in this case at the left hand side negative values should be marked above the datum. At the right hand side positive values should be marked above the datum. Why? Because we are following different sign conventions in the bending moment as well as the joint moment. Similarly, for the right span we have minus 75 and 0. So you linearly connect these ordinates. So above this you superimpose the bending moment diagram due to applied load. For the first span it is linear, and second span it is a parabolic, simple parabolic. So now finally we have obtained the bending moment diagram. Then further you can calculate the positive bending moment at the span as well as the point of counterflexure, the distance of point of counterflexure, by applying the equilibrium conditions. That is, the moment at the span is equal to 0. You take some distance x from the left support or right support, substitute, write the moment equation at a distance x from the support, then equate it to 0.